The ocean gives us life. It supports trade, transportation, tourism, fishing, energy production, and millions of livelihoods around the world. It shapes economies, regulates climate, and connects continents to promote businesses, tourism, and commerce while fostering regional development through trade, transportation, infrastructure, and economic connectivity. But the same ocean that sustains us on one hand can also threaten us on the other hand. Across Africa and around the world, rising sea levels, stronger storms, and coastal erosion are threatening homes, infrastructure, and entire communities. But behind every protected shoreline, there is engineering. This is the story of how civil engineers fight the sea using science, geomorphology, hydraulic engineering, and coastal structures to defend the land against one of nature's most powerful forces. Coastal defense refers to the engineering structures, systems, and interventions designed to protect coastal areas from erosion, flooding, storm surges, and wave attack. The core purpose of coastal defense is to prevent erosion by stopping waves from washing away shoreline sediment. Another purpose is to protect against flooding by shielding low-lying coastal areas from storm surges. Coastal defense also serves as asset defense to safeguard critical infrastructure, homes, and coastal economies. Before engineers design any coastal defense structure, they first undertake feasibility studies. This involves coastal geomorphology. Geomorphology is the science of how landforms are created and the physical, chemical, and biological processes that cause them to change over time. In coastal engineering, geomorphology helps engineers understand how coastlines naturally behave. Because coastlines are not fixed, they are constantly changing due to wave action, tides, ocean currents, sediment transport, river discharge, wind activity, and changes in sea level. Some coastlines naturally erode, while others naturally accumulate sediment. Engineers study beaches, dunes, estuaries, lagoons, cliffs, and delta systems to understand how the shoreline evolve over time. If engineers ignore coastal geomorphology, a defense structure may solve erosion in one area while creating even worse erosion somewhere else. The ocean applies multiple forces on coastal infrastructure. These include wave impact forces, hydrostatic pressure, hydrodynamic pressure, tidal variation, storm surge loading, sediment transport, and longshore drift. Every wave carries kinetic energy. When waves repeatedly strike the shoreline, they gradually remove soil and sediment particles. This process is known as coastal erosion. Over time, erosion weakens foundations, collapses embankments, damages highways, and threatens entire coastal settlements. In engineering terms, coastal defense is about energy dissipation, structural stability, hydraulic performance, sediment management, and long-term durability. Climate change is increasing coastal instability. Sea levels along Africa's Atlantic and Indian Ocean coastlines are rising year after year. Storm surges are becoming more powerful and more frequent. Warmer ocean temperatures are also fueling stronger cyclones. In the year 2019 and 2022, the cyclones that struck Malawi, Mozambique, and Madagascar caused severe coastal flooding, erosion, infrastructure damage, displacement of communities, and major economic losses. The disasters highlighted the growing impact of climate change and the urgent need for stronger coastal defense and climate-resilient infrastructure. As sea levels rise, wave attacks reach further inland. This increases erosion, flooding, overtopping, and structural loading on coastal defenses. Many existing structures were designed using historical wave and sea level data, but future conditions may exceed those original design assumptions. To respond to population growth, urban expansion, and coastal threats, several African countries are reclaiming land from the sea. One of the most famous examples is Eco Atlantic in Nigeria. Built on reclaimed land from the Atlantic Ocean, the project combines land reclamation with a massive sea defense system called the Great Wall of Lagos. The project aims to protect Lagos from coastal erosion while creating space for housing, business, and infrastructure. Egypt has also undertaken major coastal expansion projects along the Mediterranean and Red Sea. Morocco and South Africa continue expanding ports, waterfronts, and coastal infrastructure. In Ghana, projects such as the Tema MPS Port Expansion Project combine dredging, breakwaters, marine engineering, and coastal protection works. One of the most common coastal defense structures is the seawall. Seawalls are designed to resist direct wave attack and protect land behind the shoreline. These structures are commonly built using reinforced concrete, sheet piles, gravity wall systems, or armor stone. But designing a seawall involves far more than simply building a wall beside the ocean. Like any other retaining wall design, engineers must analyze overturning stability, sliding resistance, bearing capacity, uplift pressure, toe scouring, and long-term corrosion. Sea salt is highly aggressive to reinforced concrete. If chloride ions penetrate the concrete cover, steel reinforcement begins to corrode. That corrosion expands internally, causing cracks, spalling, and structural deterioration. Another major coastal defense system is the breakwater. Unlike seawalls, breakwaters are usually constructed offshore. Their purpose is to reduce wave energy before waves reach the shoreline. Most breakwaters are built using core rocks, filter layers, and very heavy armor units. Some projects use specifically engineered concrete units such as tetrapods and acropods. These are specially designed precast concrete units used in modern coastal protection systems. Tetrapods are large, four-legged precast concrete structures placed along coasts and breakwaters. Their shapes help them to interlock naturally, reducing wave energy and preventing displacement by strong waves. Unlike tetrapods, acropods are designed to work efficiently in a single armor layer, making construction more economical. These interlocking units dissipate wave energy while improving structural stability. Engineers use hydraulic modeling and coastal simulations to determine armor size, crest elevation, wave runup, overtopping risk, and toe protection requirements. Not all coastal defense structures are designed to stop waves directly. Some are designed to manage sediment movement. Groins are rigid hydraulic structures built perpendicular to the shoreline to curb coastal erosion by trapping sediment. They are typically made from wood, concrete, or rock. They are built in different shapes depending on the coastline conditions, wave action, and sediment movement. Typical shapes include straight groins, T-head groins, Y-shaped groins, curved or hook groins, or L-shaped groins. Their purpose is to interrupt shoreline drifts and trap sediment moving along the coast. By retaining sediment, groins help rebuild beaches naturally. Revetments are sloped structures made from large armor rocks or concrete units. The concrete units are precast elements that come in different standardized geometric shapes, each designed with specific hydraulic and structural performance goals. Examples include tetrapod, acropod, core lock, dolos, X-block, cube or modified cube, antifa cube, and more. Unlike vertical seawalls, revetments absorb and dissipate wave energy gradually. Geotextiles are often placed beneath coastal defense structures to prevent erosion of soils underneath. In areas with less aggressive wave action, geotextiles can also serve directly as coastal defense systems. These materials are commonly made from natural fibers, making them biodegradable and environmentally friendly. Coastal engineering involves major geotechnical and environmental challenges. Many coastal soils are weak, saturated, and highly compressible. Engineers investigate settlement behavior, liquefaction risk, slope instability, and foundation performance. Scouring remains one of the biggest threats because moving water can remove soil beneath structures. To reduce this, engineers use riprap, concrete aprons, sheet piling, and geotextile stabilization systems. Beach nourishment projects pump sand back onto eroded coastlines to restore natural protection. Mangrove restoration is also becoming increasingly important because vegetation naturally reduces wave energy while protecting ecosystems. Across Ghana and West Africa, coastal erosion threatens livelihoods, businesses, critical infrastructure, and entire communities. Projects such as the Ada Sea Defense Project, the Keta Sea Defense Project, the Brekusu Sea Defense Project, the Cape Coast and Discovery Coastal Protection Projects are helping reduce erosion and flooding. These projects combine revetments, groins, breakwaters, and shoreline stabilization systems. At the same time, coastal engineering is creating opportunities for tourism, trade, urban expansion, and economic growth. The United Arab Emirates have demonstrated how waterfront engineering and coastal infrastructures can generate major economic returns. But coastal defense projects are expensive. They require long-term funding, technical expertise, maintenance planning, and political commitment. Africa needs more coastal engineers, more marine scientists, more research and innovation, and stronger climate resilience policies. Programs like the West Africa Coastal Areas Management Program, supported by the World Bank, are already investing in coastal protection across the region. But the scale of the challenge continues to grow faster than current investments. The engineering challenge is no longer simply stopping erosion. It is designing smarter, stronger, and more sustainable coastal infrastructure for future generations. The battle between the land and the sea never stops, and climate change is increasing the challenge. For civil engineers, geomorphologists, and coastal scientists, coastal defense is becoming one of the defining infrastructure challenges of the future because behind every protected coastline, there is engineering, and behind that engineering are the people working to hold the sea back.